Welcome back to ECE 320A, Unit 9, and in this video what we want to do is graphically evaluate the frequency response at a particular frequency, omega naught, and that omega naught is selected based on the frequency of interest or the frequency we're interested in, which is typically what is the frequency of the exciting signal that's driving our system, or what is the input's frequency of oscillation. How are we shaking the system? The output will shake at that same frequency if H of S is stable, has all of its poles in the left half plane. Then for this linear time invariant system, we shake it at a frequency omega naught. The output will shake at that same frequency. Its amplitude will be adjusted by the magnitude of H of j omega naught, and its location in time will be influenced by the angle of H of j omega naught. That will introduce a phase shift. What we want to do then is compute Y steady state of t after the transients, and the transients don't take very long in an electrical system. They take 5 time constants, and in this class we've agreed we'll just approximate the dominant mode to be that pole that is closest to the imaginary axis, assuming all of these poles are in the left half plane. We pick the poles that have the real part smallest relative to the imaginary axis, or which ones are closest to the imaginary axis. That will give us our pole distance, or sigma, and the tau, or the time constant, is 1 over sigma, and we take 5 of those to determine what is an infinite length of time, or what effectively is an infinite length of time in this particular system. Let's now find the sinusoidal steady state of an output if we are given an input signal that's 2 cosine of 6t, and our our transfer function, h of s, is 30, s plus 1 over s plus 10. This transfer function is in pole zero form. That's the form we need it in order to sketch these contributions due to the zero factor and the pole factor. And in fact, we can very easily identify the locations of the poles and zeros because of this factored form. We have a 0 when the numerator vanishes, or for those values of s, finite values of s, where the numerator vanishes. In this case, it vanishes at s equal to -1. The poles are those values of s that cause the denominator to vanish. In this case, s equaling -10 causes the pole to vanish. There is now our pole zero pattern for this transfer function h of s. Now we need to find h at a particular frequency, and the frequency that we want to evaluate h of j omega at, again, we are interested in walking up the imaginary axis. That gives us our frequency response behavior. How does this system behave to being excited by particular frequencies? Or if we shake the system at 3 radians per second, then we would be interested in its frequency response, or magnitude and angle at that frequency. If we shake the system at 6 radians per second, which is in fact how we are shaking it in this example, then we want to evaluate the contribution of the zero factor, the pole factors, and the gain. In this case, we now have a distance from the 0 up to J6, and we have the angle that I will call theta sub z. This distance is L sub z. We have the contribution of our pole factor, which is L sub p, and we have its angle, theta sub p. We now want to compute those and not forget the gain constant of 30 when we're computing the contribution, or the magnitude and angle, of this transfer function h of s at j 6. 6 radians per second, and again, we're marching up the imaginary axis. That is associated with an oscillating input signal that has poles at plus and minus J6. We now want to find H of J6, which is 30, LZ theta sub Z over L sub P theta sub P. And I'm not sure why I subscripted Z with a 1, so let me erase that. Or we now have 30 times L sub Z, and L sub Z is going to be the hypotenuse of that right triangle, which has a horizontal distance of 1 and a vertical distance of 6. We're looking now at the square root of 37, which is about 6, a little bit more than 6. We have L sub P, which is the hypotenuse of that right triangle, which has a horizontal distance of 10 and a vertical distance still of 6. Or we're now looking at the square root of 136. This now is a little bit bigger than 11, so this is 11.66 and a little bit less than 144 square root, which is 12. So those are looking right, and now we have 30 times 6.083 divided by 11.66. The angles, theta sub Z, again, all of these angles are measured with respect to this horizontal, virtual horizontal line that extends to in the positive horizontal direction from each of these pole and zero factors. Theta sub Z, I guess I continue to want to subscript that Z, but that's theta sub Z. That now has an angle such that the inverse tangent of 6 over 1, the inverse tangent of 6 is 80.54 degrees. Theta sub P, now we're looking up 6 and we're looking over 10. We're not quite looking up 10, so this is less than 45 degrees. If hopefully we find that this angle of inverse tangent of 6 over 10 is less than 45, it's in fact 30.96, and we now can introduce those angles. We have an angle of 80.5 and an angle of 30.96. Such that H of J6, multiplying all of those numbers together, are 15.65, and we have an angle of theta sub Z minus theta sub P. We algebraically sum those, and 80.5 minus 31 ends up being an angle of 49.57 degrees. So that this complex number, H of J6, can immediately be used to determine our sinusoidal steady state output. We started with an input magnitude of 2. H is now bumping that up by a scale factor of 15.65. We're oscillating at the same frequency that we were being shaken initially, which was 6 radians per second. There was no phase shift in X. And now we simply introduce the phase of our system, which in fact is a plus 49.57 degrees. This is now our sinusoidal steady state output. This would be in effect after the time constant of our dominant mode. In this particular case, we only have one pole, and its real part was influenced by e to the minus 10t. This is now e to the minus t over tau, and this now says that tau is 1 over sigma, which is 1 over 10. And so now after 5 tau, or after 1/2 of a second, we will be moving in the output at about 31 amplitude cosine of 6t with a phase shift of a little bit under 50 degrees. That's now how we can start to think about what's happening when we shake a system at a given frequency. The output will be a slightly modified in amplitude or big modification, depending on what H is, what it's doing at that particular frequency of oscillation. In this case, it's 6 radians per second, and a shift in time.